we're in the final stages of this tournament. So this finals, after which we will have the closing ceremony where the awards will be where the award ceremony will also be. So please, let's welcome the participating teams in the finals. So, Hungarian Team Green. Team Organization. And Hungarian Team Red. I wish you all good luck. And yes, so let's open this final stage of this tournament. So, Lily, please, thank you for being the moderator of the finals.
Well, thank you for the honor. First of all, I would like to begin by asking the jury members to introduce themselves. So, from the left, please stand up, state your name.
Hello, I'm Giga. I'm from Tbilisi, Lithuania. And I am a student of Tbilisi State University.
My name is Zepaleshin, PhD, radicalist and founder of the International
Congratulations for reaching the finals. I'm David, and I'm master student of bioengineering at the University of Tbilisi.
Hello everyone, my name is Stefan Mikiu, and I'm a bachelor's student at the University of Bucharest, Romania.
Hello, my name is Michael Forlova. I'm researcher in Agricultural University, Georgia.
Thank you very much. So now let's begin the round. I would like to start by asking the teams to decide on the order of their choosing. So first, I would like to ask the captain of Hungarian Team Red to state at what place they would like to choose their column.
We would like to choose second.
Second. Thank you. Now I would like to ask the team captain of Nush to state what place they would like to choose their column.
We would like to choose first.
First. This leaves Hungarian Team Green to choose third. Now I would like to again turn to the team captain of Nush and decide on their column.
We would like the last column.
Thank you. Now from the team captain of Hungarian Team Red.
We would like the second column.
Thank you. And this leaves Hungarian Team Green to be the first column. Before we begin, I would also like to add for the participants that during the report at 7 minutes, when you have 1 more minute left, I will stand up to say your names. And so now, I would like to ask the reporter from the Singaporean team to come to the front, and let's begin.
testing. Testing, testing. Testing, testing.
Okay. So please, whenever you're ready, please begin.
Good afternoon, judges. I am Maharshi from Team Organoshan, and today I am honored to present on problem 6, analog computer. So first, a brief overview of my solution. I have decided to provide a molecular scale implementation of reservoir computing, a specialized type of computing that is used for machine learning and prediction tasks. It has a huge range of applications from facial recognition to weather prediction. More specifically, I have decided to do a molecular scale implementation of using vibrational energy redistribution within a molecule for a simplified weather prediction task. So, for example, given temperature and humidity data, can we accurately predict the chance of rain? So there are 3 main steps to this. Number 1, excitation, where we excite the electronic and nuclear vibrational modes of our molecule using lasers that are tuned to specific frequencies following our inputs. Next, we give it 2 picoseconds for the actual nonlinear computation to occur, where it redistributes from excited states down to lower energy vibrational modes. And finally, using a detector, we can measure the energy level at different positions, and from that train our model to be able to better predict the probability of rain. So more specifically, using data points, we can train and teach our model to be able to better fulfill this task of predicting the probability of rain. So now I will start off by elaborating on what reservoir computing is with a simplified analogy of, pretend for example there is a spring network. So our input is essentially we excite a specific part with an input force F, and then we let it redistribute across the molecule, providing a source of a nonlinear computation in the reservoir. Then we measure the resulting force at 2 different locations, multiply them by some arbitrary weights, W1 and W2, and add them up to get our overall output. Now, the last step is essentially a linear regression step where we can change these weights, W1 and W2, to better train our model, like for example here, this model, to better fit the data points that we've trained it with, so it can more accurately predict the chance of rain. Now, I'll talk more about the molecular concept behind this. So, drawing analogy to the earlier mentioned spring model, I've decided to use para-azidobenzonitrile, which is an organic molecule with a total of 48 normal vibrational modes, allowing it to act as a highly nonlinear reservoir for this system. Sorry, give me 1 sec. Okay, now to elaborate more on the excitation step, we do something known as vibronic excitation, where we use pump laser pulses to excite our our molecule both in terms of electronic modes as well as nuclear vibrational modes. Hence, there's a large excess of energy. Then we give it 2 picoseconds for the energy to redistribute from higher energy excited states to lower energy nuclear vibrational modes. So this acts as a nonlinear reservoir for computing purposes. Now, more on the detection step. Essentially, this is based on a model known as pump probe spectroscopy, where we shine IR lasers of these 2 frequencies that are designed to probe specific energy levels for specific vibrational modes. And we can set them to arbitrary intensities I1 and I2, for example. And the important thing to note here is some of it will be absorbed for further excitation, while the rest is transmitted straight through. Mathematically, it has been shown that the amount that is transmitted straight through is proportional to the average energy level at the vibrational mode that we are probing, multiplied by the intensity of our probe pulses, so I1 and I2 as I mentioned earlier. If we set up a detector to measure the total intensity, it's essentially adding up IT1 and IT2. And what this does is, following our equation that I provided earlier, this is actually doing our weighted addition step for us, where the output of our reservoir is the average energy level at the 2 vibrational modes we're probing, and the weight that we should be changing is the intensity of our probe laser pulses. Now, I'll give an overview of my entire solution as a whole. So let's first define the problem clearly. More specifically, given 2 input values, temperature and humidity, can we accurately predict what is the probability of rain? So to do this, we need data points like shown in this slide. So essentially, this is an overview of my solution. I'll go through it step by step. So first, as mentioned earlier, we do vibronic excitation of electronic and nuclear vibrational modes by shining lasers of frequencies that are tuned to our input values. Next, we give it 2 picosecond delays for it to actually do the computation on a molecular scale, as each chemical redistributes the energy through this phenomenon known as intramolecular vibrational energy redistribution, or IVR, doing our actual nonlinear computation itself. Next, the next step is to essentially probe it or detect the energy levels using, as I mentioned earlier, probe laser pulses with arbitrarily set intensities, I1 and I2 for example. And as mentioned earlier, the total intensity detector will then measure the total output, intensity rather, which is actually doing this weighted addition step. However, since our model is not yet trained, it may not give us an accurate value. Like for example, even though it's supposed to be 1.0, meaning it's supposed to rain, it might give us a value like 0.4. So how do we train this? Now the training step essentially relies on a process known as gradient descent, which is a common linear regression tool used in reservoir computing. So this is a slightly complicated equation, but essentially what it involves is we change our weights, which is the intensity of our probe lasers, to better train our model and teach it to better fit the data points that we are training it with. And essentially this is an iterative method where we feed in the next data point, the second data point, and change the weights again. Then the third data point, change the weights again, etc., etc. So in this step, the probe intensities can be adjusted over iterations to fit the reservoir and optimize our predictions. So lastly, just to give an example, we do something known as validation, where essentially given, for example, temperature and humidity values, our reservoir computer should be able to accurately predict the probability of rain. Like for example here, saying that it will not rain. So now an overall summary of the solution that I'm proposing for this design. I have proposed a novel design that has not been applied completely in literature before, which uses reservoir computing with individual molecules and the nonlinear phenomena of intramolecular vibrational energy redistribution. And I believe it satisfies the problem statement. As number one, it is analog as it uses continuous and input and output intensity values, and hence it can be used for a continuous data set. I believe it is mechanical as it uses the concept of nuclear motion and energy dynamics within a molecule. And ultimately, quantum mechanics is mechanics, so it is mechanical. And lastly, I believe it is a chemical scale as the nonlinear computation itself is being done by individual molecules themselves, hence satisfying that problem statement requirement. In conclusion, I have proposed a novel design for reservoir computing for machine learning and prediction tasks, like a basic weather prediction task using individual molecules and pump probe UV IR spectroscopy. And with that, I conclude my presentation. Thank you for your time, and I look forward to points by the opposition.
corner, the minute is over. Please, whenever you're ready, signal to me. Begin your time.
Dear jury, fellow participants, my name is Tamás Soldos, and today I represent Hungarian Team Green. It's my honor to oppose this presentation. First, I would like to thank you for your job. I see there is a lot of effort in it, and you gave us a very original solution. However, I still have some concerns that I need you to elaborate on. First of all, I would like to challenge the model you used, because I assume that you used the simulation proposed by Lawrence, who, however, instead of two, he suggested three variables that could be arbitrarily changed. However, you only gave us two, namely temperature and humidity, and this is why I'm concerned whether even this oversimplified model would not give us accurate prediction. And regarding this concern, I'm also interested what nonlinear differential equation is described. What differential equation describe your nonlinear computation and how it correlates with predicting rain. You also gave us the probability of the rain, and to this my question would be, it is the same probability as you see when you see a forecast or not, because I have some further questions regarding that. Now I would like to turn to the technical part of your solution. So you told us that you would excite your molecule, and I'm interested in the exact input of your system, because I'm concerned that your molecule cannot be excited by any any frequency, thus limiting your solution to discrete values. And you mentioned that you would measure the state of your system after 2 picoseconds. However, I'm not quite sure that it can be easily done, and I'm interested how you would measure this tiny amount of time. Also, you did not elaborate on the molecular orbital explanation of your excitatory system. I think these were my major concerns, and I would like to elaborate on the model of your chosen, and especially emphasizing the differential equation that would give the same result as your prediction. Thank you for your attention.
Thank you. Before we begin, I'll then give the microphone here. Also, please, whenever you're ready, signal please whenever you're ready.
Firstly, I would like to thank the opposition for raising such relevant concerns and flaws regarding the proposed design. However, I believe that my proposed report has actually accounted for many of these, and hence I would like to address them now. Now, the first concern that was raised was with reference to, I believe, a specific citation. that use a total of 3 variables as input. However, I would like to highlight that in my system, I would like to highlight that reservoir computing is a very generic model that can be applied for theoretically an infinite number of variables. It's just a matter of how you implement it. In my system, I chose to implement just 2 variables to highlight how it can be used for a simple system like, for example, weather prediction. However, by right, you can actually expand the number of lasers that you're exciting it with to a very large number. Although I cannot place an exact limit, I would say that you can actually, since there's a total of 48 vibration modes that you can excite, actually more than 48 lasers that you can use for input. The only thing that matters is you tune your intensities according to what is used to train the system. Additionally, I would like to elaborate on the concern raised regarding the exact nonlinear function that this solution is providing. So if I could refer to my backup slides now. So just to give an overview of exactly how reservoir computing works, is reservoir computing assumes that a nonlinear function, f, can be split into another nonlinear function, f, g, as well as a linear function, let's call it I. So essentially what it does, so fx is equal to g of I of x. So essentially what it does is it only meddles with the weights of your linear addition step, which is the function ix. And the beauty of reservoir computing I would like to highlight is actually you don't need to explicitly know how nonlinear your system is, as long as you can show that the system is indeed nonlinear, meaning as you change your inputs linearly, your output changes nonlinearly. It is sufficient to be used for reservoir computing. In fact, I would like to cite a wide variety of literature sources that have not only stated this, but have also shown it using a combination of computer simulations and other physical implementations of reservoir computing. I would also like to address another concern regarding I believe it was concern of how the idea of predicting rain has already been done in the system of forecast system. However, I'd like to highlight that a lot of forecast systems, like the one you see on your smartphone, is usually a result of machine learning. So essentially what I'm doing in my method is I'm proposing a new way to do machine learning and prediction tasks using individual molecules. Hence, I believe it still satisfies the problem statement. And I realized another issue was raised is how exactly is the input decided, and I would like to highlight on that now. So just give me 1 sec. Yes, okay. So essentially this depends on something known as input processing. Input processing essentially means that given, for example, a temperature and humidity value, you have to first normalize it to the range you're talking about. Like for example, let's say that your temperature range can go from 0 to 100, because I do not believe that it goes above 100 in any place on Earth. And once that is done, we normalize it to a range, and then we apply or rescale that range to the range of the UV excitation that we're dealing with, to 2100 to 2220. And I can elaborate more on why exactly this range is used later in our debate. And I believe another concern was raised regarding how is it possible to measure energy differences in only 2 picoseconds. I would first like to cite that lasers, since they depend on light, they're actually extremely fast, and this is merely dependent on the instrument you're using and its reliability. In fact, I would argue that the citation that has investigated the dynamics of IVR, or the vibration energy redistribution, has used a unique system of lasers and has shown that 2 picoseconds is actually sufficient for the lasers to work with. And I believe I've run out of time, so I guess we could talk more during our debate. Thank you.
see any mathematical model or anything that would support the claim that this system will actually represent or predict the probability of rain?
Okay, thank you for that question. I can address it now. So number one, I want to highlight that I am in fact proposing a new solution to this, as although reservoir computing is a common computational model, applying it to a physical implementation is something that has been applied in many, many different possible implementations like the spring model I highlighted. And I believe this is novel application of it, as it has not been reported in the literature before. Now I would like to talk more about...
I mean, I understand that it is original solution. However, I'm not convinced that it can be applicable to rain.
Okay, so thank you for that concern. Although I do admit that usually providing a complete analytical solution of this is complicated, as it is quantum mechanics, and in this specific molecule conducting not kinetics, but time-dependent studies of how the vibrational dynamics occurs is tough. I can provide several theoretical equations and concepts that can better elaborate on why this is nonlinear and works for reservoir computing. So, okay. So first off, I would like to talk more about the exact mechanism of intramolecular vibrational energy redistribution. So essentially, once we excite it to an...
I would like to ask you to turn to the differential equation I asked.
Okay, unfortunately, I do not have the exact differential equation as, like I described.
I would like to turn to my following question. I'm generally curious what state your molecules are in, because it can raise a concern that the surroundings of your molecule can alter the composition of those.
Although I do admit that this could be a potential concern, I would like to highlight that my exact mechanism involves a solution of the molecule in tetrahydrofluorine. And if you are concerned about how the interactions between the molecule and solvent molecules as it redistributes could be an issue, I would like to highlight that a study that has looked into the vibrational dynamics of this molecule in tetrahydrofluorine has determined that the half-life required for the dispersion of the vibrational energy into the surrounding bath or the solution takes a total of 23 picoseconds, which is a much larger time scale than the 2 picoseconds I mentioned. And to add to this, I would also like to highlight that I do in fact have experimental evidence showing a clear nonlinearity in the output of the system when we excite it with different power frequencies. Thank you.
Thank you. And my next question will regard how we should convert your input signals into, like the percentages, into frequency, because I think that the part was missed out.
Okay, thank you for the question. I apologize if I skipped over that in a bit of a hurry, but I would like to now better clarify. So once we have this percentage or normalized it to this range that we're dealing with, we have to actually scale it to the range that we're dealing with, which is 2100 to 2220 cm inverse. And the reason why I use this is, actually I can refer to my backup slides, but I believe it will take too long, so I can just verbally say. The reason for this is essentially, when we do excitation is bichronic, meaning we need to do a minimum of at least electronic excitation, which is in the UV range, and partially vibrational excitation in the IR range. So based on I have used the Amsterdam modeling suite to determine the energy levels of the different molecular orbitals, as well as the vibrational spectrum. And by looking at the range, I've calculated that this is the optimal range that ranges from the minimum, which is just electronic excitation, to the maximum, which is electronic excitation plus within the complete range of the nuclear vibrational excitation.
I understand. Thank you. And just for clarifying, what is the range of temperature? Because it is a continuous range, and I'm not quite sure how it should be renormalized for this.
Okay, thank you for the question. So essentially, let's say that we are on Earth, and in a certain country, let's say the temperature can range from let's say minus 50 to 100. It's a bit of an error estimate, but let's say that's the value. So if we're dealing with, for example, 50 degrees Celsius, we have to normalize this 50 degrees Celsius to the range from minus 50 to 100. So what percentage from that range is actually fulfilled at that 50 degrees Celsius limit? And then that percentage or the fraction that we obtain, we have to then multiply it by the distance within this range and apply it to obtain the optimal frequency for our training purposes. This is known as input preprocessing, and it's a common mechanism that's used even by laptops like this. Thank you.
I would like to offer
Dear ladies and gentlemen, Martin Sabo, representing Hungarian Team Red, and it is my pleasure to give the problem statement and debate on problem number 6, analog computer. Starting with the presentational slide of the reporter, his slides were visible and easy to read, but a bit hard to follow due to the fast pace of the presentation. The slides were neatly organized and contained several illustrations and number slides, which made the understanding a bit more easier. Moving on to the presentational part, he spoke a bit hesitantly but very clearly and loudly, maintaining a steady pace and providing an entertaining speech. His task was to make an analog mechanical computer on a chemical scale, and he used reservoir computing used in machine learning to model temperature and humidity changes and predict the probability of rain. He used a spring model for the mechanical part and the excitation of light and intensity and intermolecular vibrational forces to make his method analog. I think that the scientific part was a bit hard to comprehend, especially the connection between the chemical part and the data acquisition method, and I think that made the understanding a bit hard in the end of the presentation. Now, moving on to the opponent, during his monologue, he stated several relevant questions and also some irrelevant ones. To highlight some of them, he questioned the overall model of the solution for the problem number 6, asked about the probability of the rain and the data acquisition method, raised his concerns about the technical aspects of the problem as well, and asked for a really relevant part of the problem, the differential equations and the mathematical background of the solution. In the debate, he raised his further concerns about the mathematical model. However, I think the debate part was mostly dominated by the reporter. The reporter, in his monologue and the debate, answered the questions confidently using supplementary slides. I think we saw a very civilized debate, but I think one point that was raised by the opponent and should have been asked, the mechanical aspects of the computational method, since the input and the output are digital and using electronic parts. So, in my opinion, that was a bit arguable. In conclusion, we see a very well put together presentation and a very interesting scientific debate, and the task was mostly fulfilled, and the opponent raised several relevant questions, making the debate interesting and very civilized. Thank you for your kind attention.
Thank you very much. Now it's time for trade questions. Yes, please.
Thank you for your wonderful presentation. My first question is, the main question for my side is, what is your rationale to use the exact this molecule? Maybe you mentioned this, but could you
Okay, so thank you so much for that question. The reason I chose this molecule as usually so research in this concept of intramolecular vibrational energy redistribution is usually limited to very small molecules like water, for example. But I chose to go slightly larger than that simply because of the fact that when you go smaller and smaller, the number of vibrational modes and the pathways through which energy transfer can occur decreases. The nonlinearity in the system decreases. So I look for solutions, molecules that could be large enough for there to be a large number of vibrational modes and could also be easily explained through my presentation. And I found a literature paper that had a very thorough investigation of the dynamics in this specific molecule, para-acetylmethylbenzonitrile. And I really liked the explanations they had towards why it was nonlinear and the theoretical backing behind it. And hence I decided it would be an optimal molecule for research in this report. Thank you.
Any further trade questions? Yes, please.
So I thank you for that question, number one. And yes, I absolutely agree that the training phase is essentially adjusting the weights or the intensities of our probe pulses following the equation I provided earlier. Although some might think that this sort of defeats the point of the problem statement saying that it has to be on a chemical scale, based on my interpretation of the problem statement, I believe that computation is the function that it is providing, which is a nonlinear function. And since the nonlinear function is actually being computed by individual molecules, I believe it still satisfies the problem statement. In fact, according to my interpretation of the problem statement, I would say the linear training regression model is actually not, I could, of course, because it was basically an equation that involves simple functions like addition, subtraction, etc., etc. I could, of course, come up with another solution that does all this in using a super intricate and complicated pathway, but I decided to focus more on the nonlinear computation and the novelty of that design. And lastly, I would like to highlight that even today, a purely chemical scale quantum mechanical computer is impossible. In fact, realistically speaking, usually the bulk or the important part of the computation is done by quantum mechanical methods like this, and the classical computing, which was done by the gradient descent, is essentially just to augment or supplement the exterior control of our output. Thank you.
Thank you. Any further questions? Yes, please.
Question for Tomasz. You mentioned orbital simulation. Can you please clarify a bit what
My concern was how from the excited state would go to the electron to make this nonlinear. And I needed some further elaboration.
Thank you. Further questions? Yes, please.
Okay, thank you for your question. It's really insightful. I believe, I do not have, since quantum mechanical computations, especially in large molecules like this, are usually very hard to do, I do not have a full analytical solution to completely prove that it can be used for reservoir computing. However, like my justification for why I believe it would definitely, I'm confident that it works, is that the only requirement for reservoir computing to work is your reservoir has to be nonlinear. And I believe there are several theoretical backings behind why it's nonlinear, and actually I can elaborate on it right now.
Excuse me, but we will have time for that as we're moving on to the general discussion. Okay, we have a few questions. One of them, the first one was I think there. It's there, in the back. Also, I will ask the jury members to use the microphone for the next round for their questions.
Can you hear me?
It's not audible in the audience.
Yes.
Okay, wonderful. So my question would be something which was raised already, but I think it would be very nice to pose you the question directly. So in the problem description, your task is to design an analog mechanical computer on a chemical scale. However, I'm afraid that your modeling process is completely computational and not chemical, and varying the weights and parameters is not in the chemical part of your solution, but rather is happening on a digital computer. And so I fail to see how this solution would be solving and addressing the criteria of the question, because the only chemical part of your solution is how you generate the different values for your digital computer model. So you mentioned that it would be impossible to do it completely chemically, but that doesn't make your solution any better. How do you plan to address that?
Okay, thank you for your question. So I believe that in this solution, the bulk of reservoir computing lies in the nonlinear nature of our reservoir. And as highlighted earlier, reservoir depends on this intramolecular vibrational energy redistribution in individual molecules. And hence I believe that since this important crucial part of reservoir computing is being done by an ensemble of individual molecules, it does in fact satisfy the chemical scale requirement of the problem statement. However, I do admit it is entirely a matter of interpretation of the problem statement, and hence but I still believe Thank you.
Thank you. Next question there.
Okay, so firstly, can you please go back to the spring model, which you showed us? Okay, so the spring model is usually a very rough estimation of bond vibrations, and especially it's a very bad estimation for aromatic systems, which you can see here. As in reality, these bonds are not alternating, and many of these energy results will be degenerate. And also, therefore, making the vibrational modes non-trivial. Even if you can provide exact energy levels for your model, can you please provide the exact description of the vibrational model that can give these exact solutions back?
Okay, thank you for your question. So I do admit that the drawing specific analogy behind the calculations done by this spring system and by molecules are definitely not the same as one is classical mechanics, the other is quantum mechanics. However, I would like to highlight that this animation was simply to introduce the concept of reservoir computing and how a nonlinear reservoir is used for this type of computation. I would like to highlight that, thank you for that question actually. So I would like to highlight that the exact vibrational model based on which IVR operates is essentially when you excite it, you're doing vibronic, meaning you're exciting both the electronic, meaning the probability of the electrons residing in certain molecular orbitals, as well as nuclear vibration, meaning essentially the oscillation of nucleus. And once you excite this, since the electronic excitation is UV and a much higher energy scale than vibrational energy, this means that you have a large excess of energy. And because of this large excess of energy, the energy will then fall down using these transitions, meaning between different vibrational modes, through a nonlinear function known as the Frank-Condon's principle. It is essentially describing the probability of it falling from one nuclear vibrational mode to another. And since there are many different such pathways occurring simultaneously and in a nonlinear fashion, I believe that the nonlinear aspect is still retained in this model and still satisfies the concept of reservoir computing. Thank you.
Thank you. Any further questions? Okay,
Here.
Yes, we have two more questions. We don't have time for both. Please keep it brief. We have one there.
As an organic chemist, when I work with azides, the last thing I would do is heating them up with IR, and I think anyone who heats up organic azide, repeatedly either knows more than me in some aspect or very brave. Could you please elaborate on how can you guarantee the safety of your computer? I mean that if it starts to decompose, it will give you false readings with every single time you take a measurement with the molecule, so you do not need to decompose the compound completely to render your model.
Thank you. Please try to reply to
Thank you for your question. Just to confirm, you are asking on whether the heating up by the laser will cause dangerous effects.
And the azide will decompose, in my humble opinion.
Thank you for that question. So according to the literature that I used that investigated the vibrational dynamics, they reported a minimal change in temperature allowing for the approximation of the model that they were using. And hence, I believe that the temperature increase and the heating, the extent of heating is minimal. Hence, I believe it's not a significant concern. Actually, the concentration is also very low, so I believe that the heating is once again minimal. Thank you.
Thank you. Then one final question there.
Okay, just a clarifying question. If I understood your model correctly, then you have to teach your computer what temperature and what humidity corresponds to what frequency of rain. Then how is your model computes, what is the purpose of your model? Because I feel like if we have to teach exact data sets to it, then it cannot provide any additional data that we didn't do before.
Okay, thank you. So I can actually elaborate a bit more on this. So the specific application I was talking about is machine learning. So that means you need, the important hallmark is you need a data set to train it and do the functions. However, if your question is rather to how it can do the calculations without any data points, I believe that you can simply, it's another type of model that essentially involves you change the weights, which is the intensities, to specific values that you feel describes your model the best. And then this system as a whole will be doing your nonlinear computation of a single model that you already know beforehand, meaning you don't need to train your model. And using that, you can find values from input nonlinearly. Thank you.
Thank you. The time is up.
Summary, just to see more questions.
Thank you. So in case you are done, then please, first of all, I would like to ask for the reporter's presentation remarks. Five plus, 5. Again. 5 plus, 5. Thank you. Now for the scientific part. 5 plus, 5 minus, 5 plus, 5. Again. 5 plus, 5 minus, 5 plus, 5. Thank you. Now for the opponent. 5 minus, 5 minus, 5 minus. Again. 5 minus, 5 minus, 5 minus. Thank you. Now for the reviewer. 5 plus, 5. Again. 5 plus, 5. Thank you. Now, first of all, I would like to ask for the justifications on the 5 pluses. Okay, yes. Then, excuse me, I lost track. who gave 5 pluses, but then let's start from there. Stefan, please.
Thank you. So, I found the presentation, I found that you presented a really complex solution. You analyzed a lot of aspects of the solution. It came with a really novel model. And from my opinion, it respects pretty well the test.
Thank you.
In my case, I gave the 5 plus to the reviewer because I found the review quite comprehensive. It was said everything about what happened in the presentation, opposing, and the conclusion was also quite comprehensive. The reason why I gave the 5 plus for the presentation was the presentation was excellent, easy to follow, totally understandable, and finally everything was so
I gave the reporter 5 plus in presentation part because of the same features as my colleague said, and he also have any additional slides about the question that was asked about the solution.
Thank you. And I think it's left.
Finally, me. I think I'm the 5 plus guy here because I gave 3 5 pluses. Yeah. So, first of all, it was a brave choice of the task, really challenging task, and as well very impressive approach to solve this. Despite this, it can be a bit controversial about IR spectroscopy and other stuff. We can. I can state that this is very original solution of this problem, and despite I'm quite far from quantum chemistry and this part of physical chemistry as well. I understood this completely, and that's why 5 plus for presentational part as well. As for the opponent, it was a great job, and that's why it's on 5 band. From my perspective, I gave 5 minus because it was the opposition was not confident enough, but it was really hard to oppose this problem. And 5 plus for the review because it was, in my opinion, one of the perfect reviews in a really academic manner. And also the reviewer assessed the debate really well and for this. Despite this is the first round of the final, it was really hard to give 5 classes in this round because maybe next solutions will be even better. What they will be 6, I don't know. Thank you.
Thank you very much. If there is no more for evaluation, then I think that we can conclude this round. So, a big applause to all competitors. And I believe we can issue a 5-minute break.
Come si tocca il punto perché non fa la pallone ma che poi stanno
Mit gondoltam.
Merci. Here. Because, like, if you get closer, problem and it's not high.
So this can be used for the report.
We would like to choose probably
Like, merci.
Yeah, so if I present like this, it should be good. Is this good? Good. Okay. This is audible. Alright. You can hear it from the back. Vents are bottling. You can hear it from the back.
Sen hiç aki turnaşından
Todavía no tenemos nada seguro, Coco, pero de ahí pueden hacer una respuesta de eso lo podemos hacer. El avión no, podríamos decir, podemos hacer esto, eso y esto. ¿Están de acuerdo? ¿Están de acuerdo?
Thanks for everything.
This should be good. Hey, our friends from Mexico, can you hear me? Yeah, love you.
Ellos cobran un pago de inscripción, ellos cobran una inscripción. Parte de esa inscripción se podría usar para lo demás y generalmente las delegaciones pagamos, ya viste que nosotros lo que pagamos. Entonces ellos decían, bueno, pues si sale muy caro ir a México, a lo mejor se puede el hospedaje. Entonces yo les dije, bueno, yo voy a plantear lo que México puede ofertar y si no, pues que se quede Rumanía con ella para el próximo año. Tú, ¿qué es lo que nos sirve? Los artículos promocionales podrían pagar, pues, ¿con qué van a pagar con lo que pagamos de inscripción? Aproximadamente fueron 6,000 pesos lo que pagamos. No sé, convertido en dólares o en euros, fueron 6,000 pesos lo que pagamos cada uno de nosotros, cada integrante. Con eso de comer, bueno, se supone que lo que viene incluido fue la comida, los refrigerios, nos dieron una bolsita con una camiseta, agua, de todo agua, nos van a dar las constancias de participación, los premios, eso es lo que nos dio 6,000 pesos.
Is it audible? Yes.
All team and jury members present in the room, so we can start in a minute. Please ask everyone to start settling down because we would like to continue. Please write your name on. Okay, thank you. At once, you will need the name of the opponent, so please show the comment that will be opposed. Dear reporter, please show the comment that will be opposed, and I would like to ask the opponent to comment by their name on the board.
So this is audible. Everyone from the back.
Thank you. Just a second, I'll quickly look for the opponent. Thank you. So I think we can begin.
Dear jury and fellow participants, my name is Martin Hagedish on behalf of Hungarian Team Red, and I'm glad to here to present you our solution to problem 8, gunfire material. First, I would like to introduce you to the problem. So the task was to propose a material that is hard as possible, but quickly decomposes under sunlight. We should also describe the synthesis of such compound. We should do an estimation of its hardness, and then give the mechanism of its decomposition. There are also some criteria that had to be followed, such as the trigger should only be sunlight, not heat coming from the sun. The material should be shapable and moldable, and the mechanism should rely on a chemical method. So our idea was this, to synthesize a photoresponsive polymer, add visible light-induced photosensitizers into it, describe the mechanism of its decomposition, explain the molding and shaping process, and estimate the hardness of this material. So I would like to begin with our polymer. But first I would like to talk about photosensitive polymers firsthand. So these molecules are basically sensitive to light. That means they have photosensitive groups which can by irradiation with light, they can be cleaved and release molecules or even photodegradation. Acetylsaline polymers is a really interesting property where they undergo isomerization to silicate carbons. This reaction with water will result in a bond cleavage, as you can see on the picture. There is a quite fascinating result written down in literature where they irradiated a similar compound for 30 minutes with 390 nanometer light, and the material loses its structural integrity completely. So, how can we synthesize a compound like this? So, this is the acetylsaline polymer, which is synthesized, or monomer synthesized firsthand. This is the overall total synthesis from commercially available reagents, and this is the overall yield of this reaction. And then this monomer is co-polymerized with a low-burning dicarbonate derivative with a ring-opening olefin metathesis polymerization reaction catalyzed by Grubbs catalyst. And then this reaction then could be cleaved with ethyl vinyl ether for the degradation. So the polymer degrades in solid state upon irradiation with UVA light. This is the following equation if we assume an alternating polymer. However, the most intense radiation irradiated by the sun is in the visible spectrum, so a lot of energy is wasted because only a small amount of UV can get through the ozone layer. So our solution to this was to incorporate visible light-induced photosensitizers in the polymer matrix. But I would like to begin with our choice of photosensitizers. We have 3 triple-state photosensitizers which resolve the blue, green, and the red regions of the entire solar spectrum. The mechanism of the excitation will look like this. We have our photosensitizer in its ground state, and with the light we will get to a single state by radiation, and then through an intersystem processing we will have a triple-state photosensitizer. Then an energy transfer occurs between the photosensitizer and the acetylsaline to become directly to an excited triple state. Then this can go through a 1 to 2 shift to give our silicicarbonate triplet state intermediate, which then through a relaxation and IST to get to the triplet state, then reacts with water and goes through the reactions I mentioned earlier. So, but for a better view, I would like to showcase what happens to the actual polymer for a better distance. So, we have our polymer in its normal state away from sunlight. We irradiate the polymer with sunlight, and most of the photosensitizers and some of the acetylsaline groups get excited. Then the acetylsaline groups get excited from the photosensitizer because they transfer their energy to them. Then the isomerization 1 to 2 shift occurs. Then the trapped water in the polymer matrix then will react with the carbons, forming the hemiketal intermediates, which will then break apart due to their chemical nature. With this, we have a time, the reaction time will reduce to 7 to 10 minutes per centimeter. So, onto the molding shaping process. So, the reaction is done in chloroform. The reaction is then quenched with ethyl vinyl ether, as I mentioned earlier, and we precipitate the polymer with methanol. This will result with the purification of the polymer from the catalase and some of the side products. Then we will redissolve the polymer in chloroform. We add the photosensitizer 0.3% each, and the water as well. Then we will remove the solvent by vacuum, and this raw plastic then can be injection molded. But this could be done because the polymer has a low melting point between 150 and 220 degrees C and a low mold shrinkage. I can include further detail in purposes. Also, the polymer is a thermoplastic, which basically means it softens upon heating, and this allows it to be more flexible. But how hard is a material actually? So the polymer is comprised of 2 monomers. The ratio of the 2 greatly changes the properties of the final product. But in literature they use a 1-to-1 ratio. As far as I know, the best way to come over this that in the polymer, we will end up with a 1-to-1 ratio as well of the monomers. Unfortunately, there's no data on SSI polymers properties. However, in the literature, they said it is a crystalline polymer, which means it's quite crystalline. No-bonding polymers, on the other hand, are used in rubber production. And because our polymer is actually a cyclic olefin copolymer, which is greatly described in literature, has a lot of data, such as the tensile strength, the melting point, and the sharp impact. And we give a broad range of these numbers, we have a really great chance that our polymer will fall into these numbers. So, but for a better view, I would like to sort this polymer into a hardness scale. I found the Schulze hardness scale is suitable for this problem. It had a score of 75 to 95. And this is considered to be a hard plastic, which means it fulfills the criteria because it is a hard and strong material and should withstand big mechanical forces. So, in conclusion, we propose a material that degrades under sunlight. We establish the synthesis of this compound. We added photosensitizer and water to the reaction, to the polymer to make the reaction more efficient. We established the mechanism of its decomposition, the molding and shaping process, and then we did an estimation on its hardness. I would like to thank you for your attention.
Thank you. The minute is over. Please stand up and come to the front.
Firstly, I would like to thank the reporter for presenting such a very well-designed slide. I really enjoyed the presentation because it was full of colors and animations, and I really liked watching it. However, I feel that there are a few flaws in which your solution has failed to account for, and I would like to go through them right now. So firstly, the problem statement says that the vampire material must decompose at a very quick rate. However, you have mentioned in the slides that it takes around 7 to 10 minutes for the entire polymer to depolymerize. I would like to ask whether you can justify if 7 to 10 minutes is actually the quickest in which this polymer can depolymerize. And if there are other polymers that may actually depolymerize at faster rates compared to yours. Secondly, I would like to clarify, in your presentation, if you had mentioned that if that visible light or UV light was the trigger for the depolymerization. Because in my knowledge, sunlight consists of both UV light and visible light. However, artificial lights like LEDs do not have UV light. So could your material then be potentially depolymerized by artificial light, which is then violating the problem statement in which it says the trigger must be sunlight? how you obtain the value of 7 to 10 minutes. Because there have been no calculations of the kinetics or any mathematical modeling shown. So I would like to ask the reporter to justify if he could justify the values in which he has obtained them from. Moving on, I would like to ask about the thickness of the transparency, of your material. Because if your material is not that transparent to visible light, the visible light would not be able to penetrate deep into the material and hence not be able to trigger the depolarization of the material will not be able to trigger the complete depolarization of your material. Moving on, I'd like to clarify where you obtained the value of 75 Shaw-D hardness from. Could you justify in which temperature and conditions this value was estimated from? And furthermore, in your presentation, you have mentioned that your polymer actually softens upon heating. I'd like to ask you to quantify this. How much would the material soften upon heating? Because as we know, all around the world, the temperature fluctuates quite a lot. For example, in Egypt, it could reach up to 40 degrees Celsius, and in other places like Bucharest, it could reach around 11 degrees Celsius. So I would like to ask if these temperature conditions affect the Shaw-D hardness of your material, and furthermore, will these temperatures then affect the rate of depolymerization of your material? I would also like to clarify with you about the water, you mentioned that water leads to the bond cleavage in your polymer. However, then I would like to further ask you if your polymer is actually stable in differing humidity conditions, because an increased humidity may potentially cause your polymer to have a lower, to depolymerize spontaneously without exposure to sunlight. Furthermore, I'd like to ask you if you could provide some values for the shelf life of your polymer. So, in conclusion, I have raised some points regarding the stability of this polymer. I would also like the reporter to justify the numbers he has shown in his presentation, and also provide a mathematical modeling to further support his claim, in which the polymer depolymerizes in around 7 to 10 minutes. With that, thank you, and I look forward to your reply.
Okay, so thank you for your questions. I will try to explain them one by one. So, you asked about, is it the quickest polymer that could degrade? I think the problem doesn't state that it has to be the quickest reaction possible. And about actually the quickness, that is, how can you define a quick reaction? You can say that it is it an explosive decomposition or just a quick reaction? And I think because the reaction time is way below 15 minutes, and it is considered to be a quick reaction, I think we can conclude that it is a quick decomposition as well. So I think this criteria is fulfilled. So for the UV depolymerization, yes, that is a really big concern. However, I think if you compare sunlight to artificial light, of course, the UV is the main difference between them, and I think it is more beneficial if we use up all of the visible spectrum, the most intense radiation, the most intense light that is emitted by the sun, rather than only relying on the UV. And this is why the reaction is so quick. And for further establishing this quick reaction, in the literature, they exactly used the polymer I just used, and they said that it is decomposed under about 15 minutes. And this means if we also add these photosensitizers, which have been known that it greatly increases these reactions, I can say that I think it's actually a upper estimation what I just did, because the actual numbers will be way lower than but I wanted to be more cautious about my estimations. So about the thickness of my material. So it is a big concern because, as well, this is why I used a minute per centimeter dimensions in my answer, because the reaction time will increase with the increasing size of the material. However, this is why I chose a highly a polymer that has really good, actually really good optical properties. Here you can see the cycle-olefin copolymer's optical properties, and then this is why this reaction would also occur at a much faster pace. Yes. You also asked about the sharp impact, which I don't really understand. Usually, these have a action. Usually, these are done at room temperature, so I don't find this question quite relevant. But moving on to the other one, it is substance on heating, yes, and this doesn't just occur like it is a linear change between the viscosity of my polymer, but just a quick change. This graph is not from the polymer I used, but I want to showcase what happens. So if you can see, there is a quick change between the viscosity. So that's a temperature where the material begins to soften rapidly. And I don't think this could occur at such a low temperature, such as 40 degrees C or normal conditions. But I don't think the application for this material would have any problem with that.
Thank you. The time is up. Now it is time for the debate. Time out. Yes. The time is over. Please come back. And please, once you're set, begin.
Thank you for replying to some of my questions. I found some of them satisfactory. However, I feel that most of my questions have actually been unanswered. Firstly, you mentioned that 15 minutes, a time of depolarization that is less than 15 minutes is considered quick. However, in my interpretation, however, 15 minutes is actually quite long. For example, most chemical reactions which we can carry out in the lab occur in less than 1 minute. So could you please elaborate on why you believe that 15 minutes is actually the upper limit for quick reactions?
I think because, as I stated before, the reaction doesn't have to be just what you're referring to could be an explosive reaction or just deteriorating almost instantly. But because the Rosen doesn't state that it has to be an immediate change in the structure of the polymer, I don't think this question. I think my answer for a question, your question would answer.
Okay, I do not really agree with this because I believe that a depolarization of around 20 seconds can be considered quick. However, let us move on. So you also mentioned that sunlight, that you are using visible light for the trigger, am I right?
Yes.
However, could I question you on why you do not include UV light? For example, you could use a photosensitizer, which is
UV light because the acid sign already absorbs the UV light. So not only the visible spectrum, also the UVA light will be absorbed by the polymer. This is why I said some of the acid signing groups get excited as well as photosensitizers. That might have been
Okay, so I noticed that you have some references in which you said that they exactly use the same polymer as you. Could I then question you on which part of your report is your own original contribution? And could you then justify if this is then normal?
Yes, as I mentioned earlier in my actual presentation, our solution to the low reaction time, 30 minutes or 50 minutes, was to add visible light induced photosensitizers, and this wasn't described in literature yet as with this polymer. And this is where the originality comes in.
Alright, I think your answer is satisfactory, but you have yet to reply to my question on the mathematical modeling. Could you, because you have added these new compounds into your polymer, would they then affect the rate of your depolymerization? And could you then justify with models, for example, like the Avrami equation?
Actually, I don't have any data on that, mainly because this SSI doesn't have enough data for these calculations. This is why I only did an estimation, and I emphasized just only an estimation, which is, I think, is a relatively usable in this case, because we don't have experimental data of the actual polymer, and we cannot do these calculations with this.
I see. Moving on, could I then, you still haven't replied to my question on the varying conditions all around the world. For example, some countries have higher temperatures than the others, and some are more humid. So how would the stability of your polymer, how would your stability of the polymer then differ in these differing conditions?
Of course, when you have a high temperature region, of course the polymerization will occur faster at a faster pace. And when you have a colder condition, it will, of course, be a lower pace. But I don't think the difference between these regions would have any big effect on this. However, you also asked that the sunlight. If you want to compare sunlight and artificial light, you need to use something like an industrial kind of lamp to actually get to the level of what is emitted by the sun.
You said that the difference does not really matter. Do you have any quantitative values to justify that claim?
Pardon, could you repeat that question?
You said that these differing temperatures indeed will speed up and slow down the reaction. And then you proceeded to say that these actually do not make much of a difference to the depolymerization time. Could I then ask you to provide some quantitative numbers to justify your claim?
Again, I don't have quantitative numbers, but I'm really sure that a 10 to 20 degrees difference in temperature wouldn't cause a significant, something like a 10 to 15 minute change in time, only just a matter of seconds.
Alright, I don't really agree with you on that. However, could you then elaborate?
I would like to ask you to elaborate on that.
Excuse me, we will not have time for that as the time is over now. So I would like to ask the reviewer to stand up, come to the front. Write her name up on the board, and whenever she's ready, please say it.
Jury. My name is Anna Kohara, and I am here on behalf of Hungary and Green to review this presentation and debate about problem number 8, vampire material. First, I would like to congratulate both the reporter and their opponent on their work. I believe you could see an interesting debate about the problem. To begin, I would like to start with the reporter. About this presentational part, his slides were aesthetically pleasing, neatly organized, and they maintained a logical structure, which made the understanding as easy as possible. His satisfyingly elaborated one, as pointed out by the opponent. The opponent's speech and presentational style were clear and understandable, and it was quite confident. Most of the questions he asked were relevant, however, he had some irrelevant questions as well. Most of his questions were regarding the polymerization rate of the polymer, and he also asked for some numerical data on this. He also questioned the stability of the polymer in different humidity and temperature conditions. However, I believe that some extra information could have been asked about the molding process of this polymer. The main flashpoints of the debate between the opponent and the retorter were, again, the time of decomposition and the stability of the polymer in different conditions. The opponent also questioned the originality of the solution in the debate. In conclusion, I believe we could see an interesting and scientifically fruitful debate where both participants fulfilled the criteria of their roles. Thank you very much for your attention.
Thank you very much. Now it is time for jury's questions. David, just a second, the microphone will be taken over.
Hello? No, cool. I'm wondering, adding those
photosensitizers.
Yes. Photosensitizers affect the structure or overall appearance of the polymer in any way. Research that's one. And secondly, do you have done any work on the amounts of those additives, and how do they affect the kinetics of the composition and so on?
Okay, so the polymer would have an appearance as, I think, a brownish color because we have most of the light absorbed, and some of the blackish material that is transparent. This might sound strange, but there are transparent materials that are black, so there's a full answer, I guess. But also
about structural integrity of the compound, that's one. And the second question is how does the amounts that you add of those additives affect the decomposition rates, and have you calculated the amounts that you would add?
Yes, so I included water and the photosensitizer in the mixture. Originally, they didn't include the water. That was to increase the phase of fastness of the reaction. But I only didn't want it to go over the threshold. That would mean that the polymer would be, the polymer's properties would change. At least 0.1% would be lower than that number. So the water wouldn't change the properties. And the same applies to the photosensitizers, because the concentration is around 0.9% if we consider all of the dyes, and that is the number that still doesn't have any impact on the structure of the physical properties of the material. And the reaction time will be increased because of course, the light will be absorbed. And I shown a slide in the discussion where I shown you that these photosensitizers has a number called the quantum yield, and these numbers indicate how much of the light absorbed will be brought to the reaction I mentioned earlier. And with these numbers, these are 68% for two and 53 for the other one. These numbers are high enough that the reaction time would be at least half of the original one.
Thank you. Further questions from other jury members?
Thank you for your presentation. Actually, I had also a question about photosynthesizers. My question was already answered. I just have one clarifying question. Did
Yes, all of these
And
are.
they are red, green, and blue because we will add them together or separately, or these are three options.
Oh no! In my presentation, I said I use all of these dyes together in the polymer, and I shown the colors only to indicate what wavelength of color, what color will be absorbed. This is not the color of the material or of the, but what is absorbed.
And you are sure that these molecules will not interact chemically with your polymer and between themselves as well.
Yeah. Yes, that's right. I try to find a photosensitizer that is chemically resistant. And they also, in there were studies where they conducted experiments to find out the decomposition of these dyes throughout the injection molding, which is a high temperature. And the temperature required for the decomposition was way higher than what we need for the molding process.
Thank you. Do we have any further jury questions?
Monomer synthesis.
Which one? The acetylene? Or the, okay.
In the meantime, we are stepping into the general discussion.
The reaction starts from the most commercially available reagents, and these are well-established reactions.
I have a question about what arrangement to go in darkish.
Yeah, this reaction doesn't occur because this is only initiated by the UVA light, the photogroup rearrangement, and the mechanism is the light is this basically. As you can see, the excitation only occurs with UVA light, and we say that heat doesn't have the properties, of course, to trigger this reaction.
Thank you. Can we move on to the next question? Okay, then there, the first one. Yeah, there, please.
To the opponent. In the discussion, there were a few sentences about the sharp impact measurement. So I would love you to explain the validity of your concern regarding the temperature conditions of the Sharpie measurement by describing how a Sharpie test works.
Thank you for your question. So I was concerned about the Shorty hardness measurements because he had initially said in his report that high temperatures actually softens his material. And I was thus wondering if when performing the Shorty hardness test, whether the indenter, when it indents into the material, would the distance then be increased, and thus proving that the material is actually much weaker. Does that answer your question?
Yeah, absolutely.
Thank you. Thank you. The next question was there.
Hi, moderator. May I ask two questions to the reporter?
One, please.
Yeah, one, sure. Just now the opponent raised an unaddressed concern on how the photosensitizer can be activated by visible light, which allows this material to depolymerize even under artificial light, which typically has an intensity of mid-morning sun. Hence, how does your entire material satisfy the common statement that sunlight has to be the only trigger? Thank you.
If you think about it, sunlight is a really strong source of light, of course. The whole light in the whole place in this room is lit by even through windows and filters that we have. And if you think about it, artificial light doesn't have enough energy under emission to trigger this reaction. Of course, the reaction will be triggered, but at a really much slower pace. And with this, the sunlight should only we can say that the sunlight will trigger the reaction with these pace. So I think I answered the question.
Thank you. There is the next question.
Okay, so question to the opponent. You claim that chemical reactions usually happen under 1 minute. This was one of your main concerns when addressing that the reporter, the opponent's question or their interpretation is not correct. But I'm quite sure that especially organic reactions take off hours to complete. And you offer an organic material that decomposes beautified under 1 minute.
Sure. So actually, if you use 50% polyphenoldehyde co-butanol mixture together with 50% polycaprolactone and including ITX photosynthesizer, it's actually been shown in literature to depolarize under 50 seconds.
Excuse me, I would like to ask the jury members to disregard the question and the answers. I would like to stick to this solution model. Are there any further questions?
Can I have a reaction to this one? Because I think this is...
In case you're asking.
Okay, so I think this is borderline alternative solution, but how can you... I want you to elaborate how can you do this exactly with my polymer? Because you have the answer.
Sorry? Because his question was for me to propose another organic material that could depolarize under 1 minute.
Yeah, but you suggested a new solution to my problem, to my...
Thank you, and excuse me, but I will now ask to conclude this debate now right here, and ask the jury members to write down their answers. Okay, in case if every jury member is ready, then I would like to first ask for the presentation on this. Five plus, 5 plus. Again. 5 plus. Thank you. Now for the scientific. 5 minus 5 plus 5. Again. 5 minus 5 plus 5. Thank you. Now for the opponent. 5 minus 5 minus. Again. 5 minus 5 minus. Thank you. Now for the reviewer. All 5s. Again, all 5s. Thank you very much. So first, I would like to ask for the justifications about the 5 pluses. I think we can start from there.
Okay. I give 5 plus for presentation part because the presentation was organized very well and every usage of great presentation. Thanks a lot.
Thank you.
I would like to say about the presentational part of the report that he included lots of visuals to really make it easy to follow the whole solution of the problem. And also had a really fluent speech. And moving on to the scientific part, he came up with a complex solution and paid attention to the details. And even though he wasn't able to give exact numbers, he managed to give estimations based on analyzing the literature.
Thank you.
I gave 5+ for the presentation part as well. I think had absolutely everything for the presentation, and the oratory was great. Everything was relayed to us quite good. Thank you.
Okay, thank you for this, and I would first commend my 5+ for presentational part. I awarded this this part because I wanted to notice the loads of effort in this presentation. I want to appreciate. I appreciate how much time you worked on this presentation. I suspect this was weeks or so, maybe months. And yeah, this is definitely not a last-minute presentation, and thank you for this. And for the debates, also we, as the last time, we see an example of the very scientifically, academically correct debates, and at the same time, the tension here makes us all very, very excited about this. So, thank you for this round. Any other comments? Thank you.
Just a small comment. As I understood, the originality and the uniqueness of this your project was in adding the photosensitizers, right? Yeah, and the water gas. And in this case, as well, basically what happens when they are activated, those photosensitizers, they become some sort of a catalyst for the reaction of composing this polymer, right?
Basically what happens is the energy from the lights will be basically absorbed.
Yes, yes. When they are activated, they act like a catalyst, and as this was the part of uniqueness of your project, it would be really great to include some sort of kinetics of those photosensitizers and how they work, and say mathematically calculate what would be the optimal amounts that would be added, and what amounts say their action would be saturated. But otherwise, that was the only thing I missed, but otherwise it was great. Thank you.
Thank you very much. Yes?
May I ask for a justification on the 5- marks as well?
Excuse me, there was a question regarding the 2 5- marks. I would like to ask the 2 jury members who gave the 5 minuses to justify why they gave 5 minus.
There was some weaknesses that I saw in these solutions, and that's why I ended in the openness, and that's why I gave my 5 minuses.
Thank you. Can you pass the microphone over?
I'm agree with my colleague, and I think, in my opinion, there was not enough information and data to answer the questions. Thank you.
Thank you.
Thank you as well.
I believe the round is over now, and I would like to issue a short break.
As a kid, Fossey, you don't think of information on 130 slides. Igen, ez már nem fog változtatni, de attól még szeretném megadni. Mutasson rá, hogy hol vagy a 118 diában a hiányosságban. Inkompetens és baszkalapú. Ugye? 9. Ez most nagyon bevonás. 116 most ez utána mondjon rá baszolni. Próbálom az enyémességet.
And then the opponents should comment by their names up on the board. Thank you very much. In case we are ready. Then please begin.
Esteemed jury and dear ladies and gentlemen, I'm Tbilisi from here in England, and today I will present the solution to problem number 1, chemical traffic lights. solution, and it will open up the R3 reaction phase. And more and more hydrogen ions will get produced. And that's when we will reach the top of the pH curve. When the hydrogen ions build up enough, and most of the sulfide ions get consumed, the R2 phase will open up, the R2 reaction will open up with the R4 too, and with that, even more hydrogen ions will start getting produced, and the hydrogen ion concentration will go up again. That will also get used up by the sulfuric acid. And the production of hydrogen ions will result in the plummeting of pH. And at the end, I also mentioned that we added manganese ions to the solution, and that is important because, of course, as you can see, the R4 creates twice as much hydrogen ions, or the concentration is twice as much as in the R3 ones. So we need to introduce a secondary hydrogen ion consumer for the oscillation to keep impact. And now let's alter this oscillation by choosing the indicator, and let's see the output. So, first of all, our proposed color phases are seen here. The top will be the green color, then the second or the middle pH will be the yellow, and the bottom, the lowest pH will be the red color phase. So we need to look at indicators that change change colors at around 3.8 and 6.6 pH. And I found two suitable ones for this. The first one is the ethyl orange one. This changes color from red to yellow at around 3.4 to 4.8, and it is soluble in water at around 1 gram per liter. And that is the case for the second one as well, which is in yellow. This one changes color from bright yellow to bright blue, from 6.0 to around 7.2. And if we then take both the pH color strips that we created, we can see how they look like together. So as you can see here, at the perfect pH, we can see that it changes color from red then to yellow then to green, and that means that it is perfect for this task. So our final color change scheme is seen here. So the reaction will start from green, then to yellow, then to red. That's one period. One period, as I said, lasts around 10 minutes. The color changes are at around 3.8 and 6.6. And if you look at the timing, the first one is the green, of course, which lasts around 5 minutes. Then the red will last 2.5 minutes, and the yellow one too will also last 2.5 minutes. So this means that the ratios add up as they should, so they will be ready for intersections. So let's see a simulation about how this will work in an intersection. I would like to mention that this reaction sample time is around 30 minutes. It needs that amount of time for the oscillation to start, and after 30 minutes, the colors will start appearing. So the first one will be, as you see, go from yellow, then the green starts at the other one, and we have to start the second traffic light at around 5 minutes later. So in conclusion, chemical traffic light based on the sum oscillator system would have the right color sequences in the correct indicators, and it would have 6 times 10-minute cycles of 2.5 minutes red, and 3.5 minutes yellow, and 5 minutes green movements. So I think that we both the task. Thank you for this attention.
Thank you very much. You have heard it. You have 1 minute to prepare. Your time has ended. Please come to the front.
Esteemed jury, and ladies and gentlemen, I thank the reporter for such a greatly presented and exclusive solution. However, it is my duty to point out the concerns regarding this problem. So first, I would like to start with a arguably unfulfilled criteria regarding the color change of the system. I find it quite possible that the indicators used in these solutions are bleached or shifted due to two different side reactions that can happen in this system. The first side reaction that I find quite possible happening is if the bromate ion and the bromide ion exist both in acidic conditions in the system, then as I find it quite possible that these two ions exist together, then bromine will be produced as a side reaction, and thus bromine will react as an electrophile substitution with the aromatic rings of the indicators used. And as the aromatic rings will be electrophile, will undergo electrophile substitution with the bromine, I believe it is possible that their colors will be shifted. So my question to the opponent would be, to the reporter would be, how much bromine can be produced as a side reaction, and what do you believe, what percentage of your indicators will undergo electrophile substitution with the bromine, and how would their color shift? Is this accounted for in the indicator color spectrum? Moving on to the second side reaction, it is also possible that the bromate ions would be coupled with protons to form bromic acid, which is a very strong oxidizing agent that would possibly oxidize the diazo bonds found in both of your indicators to form nitroso groups, and this way your indicators might be bleached. So my question is, how much bromic acid would be produced in your system, and can you show calculations of the concentration of the bromic acid as a function of the time or the pH, and what is the rate of the indicators being bleached by the bromic acid, and also is this accounted for in the color spectrum of your indicators. Now moving on to my concern regarding the effectivity of traffic regulation by these solutions. First of all, I am concerned by the length of the yellow phase in this reaction, as the yellow phase is 2.5 minutes, which is quite long for a traffic light. And I am also concerned regarding the sustainability length of this reaction, as that is only 1 hour. So I would like to ask the opponent whether she finds these two time parameters effective enough to use this system in case of a power shortage to replace traffic lights. I would also like to ask the reporter how much time will it take to change colors from green to yellow to red and back to green. And I'm especially concerned regarding the fact that there is no stirring in this reaction, and I find it possible that the color change would take much more time than what has been shown. And as I've seen, the
as I find it quite possible that the references that the reporter used contained CSTR experiments where there is a continuous stirring, and I'm very concerned that this solution would not work without continuous stirring, as pH oscillators usually require continuous stirring. To now move on to further concerns regarding the solution, I would like to ask the reporter about the stability of the manganese oxide hydroxide compound, as manganese is usually introduced to systems as a manganese dioxide, and I would like to ask for the conditions for the manganese oxide hydroxide stability, as I find it quite possible that it would be transferred to manganese dioxide. So I would like to ask for the conditions for stability and the standard redox potential. And with that, I look forward to your answers.
Thank you very much. You have 4 minutes to respond.
So you mentioned some unfulfilled criteria connected to the shift in color about because of growing and growing
Thank you. This time is up. Now it is time for the debate.
We would like to request for the timeout.
The time is up. Please come back to the front.
Thank you very much for your answers. Can I ask you to go back to the slide where you have the graph of the oscillation? I would like to ask whether this graph has been found in experiments or they are calculated or simulated graphs. Okay, do you have kinetic data for these graphs? Thank you. I would like to also ask that when the yellow phase is intended to be skipped, I am concerned that yellow will still appear in the traffic light for a few seconds, which is enough for causing accidents. So can you prove in any way that yellow will not appear at the steeper pH increase?
Of course. So even if you look at the curve, you can see that the jump from 6 down to 3 is steep enough that there's absolutely the jump from 4 to up to 7 is steep enough that there is no yellow. But we can also prove it through the mechanics because, as I said in my presentation, the hydrogen ion will produce so quickly, so abruptly because of that of 6 hydrogen ions producing inside that reaction that the oscillation pH will drop extremely high.
Yes, thank you. However, on that graph, the line is clearly not vertical, so I still think that yellow would appear, but let's move on. I would like to ask whether, as I understood well, there is no reagent inflow to the system.
No, there's not.
Okay, then I am concerned that as the concentrations of your reagents decrease as the reaction proceeds, then the amplitude of the pH oscillations will decrease as it does in most pH oscillators.
This experiment with the potential was conducted in a batch reactor, which has no continuous flow like the CSTR, so it would still stay the same.
Okay. I would like you to explain how the color spectrum of the two indicators together was calculated or obtained, as that was not explained at all in the presentation.
I didn't conduct any color spectrum, anything about the color spectrum, because everything happens in visible light and you can see the colors and the indicators are
Okay, while we are talking about the indicators, do you have any data on how these indicators would influence the reaction itself, as I believe your indicators are weak acids or bases, thus they will have an effect on your pH oscillator?
Their concentration is so incredibly low that they wouldn't have any kind of effect on oscillation.
Okay. Looking at the conditions of your pH oscillator, what is the influence of temperature on your oscillator? As I find it concerning that the traffic light would have to be used outside, where it can either be heated up by solar radiation or be cooled down by the environment.
So as you can see, the oscillation can happen on here very high to 60, and it works actually without any temperature in this spectrum. The experiment that I used is around 45 degrees, and of course I would solve that with different heating paths.
Test. Good afternoon. I'm Kumran Kavyadashini from Team Organotion, and I will be reviewing this problem. Firstly, the reporter presented a good solution with clear slides at a good pace and in a confident manner. A quick summary of the reporter's presentation. The general idea of it is using a pH-regulated chemical oscillator system, and she has used a bromate sulfide manganese oscillator system. She claims that the reaction lasts for an hour, and the pH range is 3 to 7. She has used nitrogen yellow and ethyl orange pH indicators, and the red and yellow last for 2.5 minutes each, and the green color lasts for 5 minutes. The opposition has also brought up some good flaws in a respectful manner. So firstly, the opposition brought up the point about how much bromine would be produced as a side reaction. In response, the reporter said that the bromine will only be produced after 60 minutes and give some evidence for it, but I personally believe that there could have been more evidence to make it even more clearer. Secondly, the opposition also brought up the point about bromate ions reacting with the H+ ions to form bromic acid. And the reporter mentioned that there are more powerful oxidants present, so therefore protonation does not occur. And I feel that this is a satisfactory response. The opposition also raised the point saying that the whole system only lasts for an hour, and this might be concerning since 1 hour is not a long time. And the reporter said that 1 hour is an extremely good measure, but I feel that it would have been better if she had given more proof or evidence to why 1 hour is an extremely good measure by maybe looking at different incidents where traffic lights have failed and how long it took in average to get back the traffic lights. And the opposition also asked about the time duration for color change, and the reporter said that the jump is not steep enough, and therefore the jump is steep enough, and therefore there is no yellow. But I think a math model could be given to further substantiate your response. And finally, the opposition also brought up the point that there is no stirring in the reaction, and the reporter said that a galvanic cell-powered low-velocity impeller can be used, but she did not mention how long it will last, and it would have been better if she had given this point. Furthermore, the opposition could have probed further because this is a power shortage, and therefore having a power source to power a chemical reaction is a bit weird, so that could have been a galvanic cell could have been used is a bit weird. In conclusion, the reporter presented a good solution and the opposition brought up good flaws. Thank you.
Thank you. Now it is time for jury questions. Yes, please. Just a second, I'll get the microphone.
So, as we are in this slide, I will start with this one. You say that it lasts 1 hour. From the graph, I can see that it lasts 1 hour at say 45 degrees. So why didn't you say that, for example, it lasts at more normal temperatures like 30, if the correlation continues like that, like up to 3 hours? In this case, it should be better to mention that it's 45. But thank you. That's my question. And just a small second one. Can we do anything to adjust those times? Are there any reaction parameters that can be adjusted to adjust, say, times of each phase?
Yes, of course. So as we see the temperature also changes, how the period will last. But we can also change the ratios, for example, of different reactants. These are just some curves where they change the bromine and the manganese ion ratios, and as you see, the oscillation curve changes, and that the period and the color timings will change as well. And of course, we can adjust we can do that only by raising the manganese ion concentration as well, because that is one of its main functions in this oscillation.
Okay. Thank you.
Thank you for this presentation. Sonia, can I ask you please to switch to the slide with the mechanism of reactions? Not this one, with the reactions. Yeah. I understand the mechanisms of reactions. However, these equations are all ionic, which I really appreciate. But can you please give me, for me as a school teacher, give me the recipe how to make this reaction? Take sulfide of, I assume, take manganese in form of that, take acid in form of that, and so on. And how much concentrations probably maybe you have this.
Concentrations that were used to make this reaction happen. As you can see, these are the main reactants, and there were no purifications done to these reactants. So only these are needed for the oscillation to happen, and of course, stirring and high temperature, and reaction will happen.
Thank you.
As I remember, alkaline metals to make this not soluble in water. And what's about manganese that it's not? I think it's insoluble in water. And also, we know to make anion can act as the beta. And what's about these compounds stability in the environment?
I see the good question. So to answer your first question, whether or not manganese ion will be able to stay inside the water and it's soluble enough, and I would say that it is, as we have seen the experiment, and also there is a constant reaction that happens. So as you can see, the R6 happens constantly, and there we can see that the manganese ion is a constant cycle. So it is always present and reacting in different ways inside the oscillation.
Thank you very much. We moved into a general discussion. Yes?
And
Thank you. I would like one question from there and afterwards from there.
Hi, may I direct a question to the opponent? So since, from the problem statement, it clearly says that the reaction mixture has to be in a closed system where no external power is supposed to be supplied. So since there's a very obvious point that for the reporter, she raised that there's supposed to be, she used an external power source, the government itself, to power the mixer, and you simply literally ignored that point. I would like to question whether you are perhaps collaborating with the reporter. Thank you.
First of all, the problem statement does not include that the problem cannot use external energy source, or it has to be in a closed system. Second of all, I do find it quite strange that the report uses an external energy source for powering the stirring. That is why I have highlighted this in the debate, and that is why I have inquired it. Indeed, it is quite strange.
Thank you. Then the next question was to the opponent. Excuse me, from the opponent.
Yes, so this reaction is sustainable for 1 hour, and if I understood well, it has a 30-minute landing time. So if a power shortage longer than 1 hour occurs, then the traffic light would actually be dysfunctional for half of the time, as when you restart the reaction, it would take 30 minutes to start the oscillation. So I would like to ask the reporter whether you have any solution for this problem.
I would say that there is a quite simple solution. We just have another available little traffic light, or just that container where the oscillation happens, and we started 30 minutes before, so when it is needed a change, we just change out those containers.
Thank you. We have time for one more question, which was raised there.
Can you hear me? Okay, so I just want you to elaborate on your original contribution to the solution, because I couldn't really see that in your initial presentation.
Thank you very much for the question. So first of all, I was the one who proposed the idea of using pH oscillation systems with an asymmetric curve, and that is also a part of an original thinking that I conducted, and I had to choose the pH or oscillator system from various different ones, and I found this one the most suitable. And then I also had to choose the proper indicators for it, considering their solubility and different factors. And at the end, I had to make sure that it would be functionable in a junction. Thank you very much.
Thank you. The time is over. So I would like to ask the jury to write down their remarks. Thank you. Then first, I would like to ask the presentational marks. Now for the scientific. Five minus 5 minus 5 minus 5, 5, 5, 5. Again. 5 minus 5 minus 5 minus 5, 5, 5, 5. Thank you. Now for the opponent. 5 plus 5, 5, 5 minus 5 plus 5, 5. Again. 5 plus 5, 5, 5 minus 5 plus 5, 5. Now for the reviewer. 5, 5, 5, 5 plus 5, 5, 5. Again. 5, 5, 5, 5 plus 5, 5, 5. Thank you very much. And I would like to ask for the justifications of the 5 pluses. Let them again begin from that side.
So thank you for the great presentation and great discussion, guys. It was very interesting. So I gave 5 plus to the presentation part and the opponent, and I will justify first the presentation part. I think the presentation was great, the oratory of it, and how it was laid out, the structure of it, and especially what I liked was the supplementary material, that you had pretty much supplement material for every question that was asked. Everything that was important to me. So thank you very much. And for the opponent, I think that overall all of the questions, almost all of the questions that was asked by the opponent were quite relevant. Although one thing I would still add that as this reaction is, well, I should say known, I would not ask questions about the inner things that go inside of this reaction, as this reaction and general this oscillator is studied and known. But otherwise, other questions that was asked I found quite relevant. Thank you.
I believe that all the opponent's questions were relevant and showed us 3 points of solution. Position was correct and scientifically justified. So thank you for the position.
Thank you very much. And then
I'm the last one. Thank you for this round. And actually, first I will start with the justification of my 5 plus for the reviewer. As for the first reviewer in this round, Kumaran made great review, and I suppose this is another example of perfect review with which fulfills all the criteria like validity of report, validity for the position review, and summary of all happened during the debates as well. And also, I think that I should explain my 5 minus. Balas, you made great opposition. However, I did not find it convincing on 100% on the 95. Sorry, that's why it was 5 minus. And yes, this was a great final stage. I don't remember the final stage on the tournament where we, I think, never had 4s this time. I don't remember at least, which makes this another example of a perfect tournament, which it should be. Thank you for this pleasure.
thank you very much. And I would like to ask a big round of coffee break.
Most egészen jól hallgatjátok.
Amúgy már leállított. Ja, ez még mindig megy. Még mindig megy azért.
Beleköszönök néha. Szevasztok.
Mindjárt nem meg lefelé. Köszönjük Judit Borsicki. Megy.
Meghallottam az előtt, a telefon előtt.
Megy, és van komment szekció is.
Sziasztok! Én vagyok Tényes, és most ezt senki, aki angolul nem tud.
Szia, anya! Halló! Akkor tegyük le!
Ez egy videóhívás így.
Jó, nem maradok, nem.
Is maradok én, hogy látok.
Oké. Szia!
Mindenkinek csak azt mondod, hogy oké, vagy rendben.
Most ez hogy kéne lereagálnom?
Nem tudom.
És akkor most a legizgalmasabb...
Hallod, jöhetnek az interjúk. Dénes, mit gondol a mai döntőről?
Igazándiból szerintem papírforma teljesült, ez egyértelmű volt, hogy ez így fog végződni.
Mit gondol Szingapúr utolsó kérdéséről, a kollaborációt illetően? Mit gondol Csernecki oppositionjéről?
Hát, ahogy Botlik Bencét idézem, darabos volt, mint a kéthetes kefir, de végül is jó pontokat kapott.
Balázs, te mit gondolsz az oppositionedről?
Megtette a hatását. Csak ezt tudjátok, hogy fönnmarad ugye a livestream. Ja, nagyon jó.
Megkérjük, hogy vágják.
Na, szóval most jön az igazán izgalmas részei az estének, ki mellett ül a repülőgépen.
Tök mindegy, mert mindenki ki lesz. Amúgy rohadtul nem működött nekem az a Red Bull, mármint hogy én majdnem végigaludtam az egész döntőt.
Nekem sem, nem szokott.